Okay, good morning. This is the 13.6 video, and I have exciting news. Thanks to someone sharing an app with me in class last night, I think I have finally found a way to post the non-converted versions of these videos online. So hopefully this is going to be a clear, good video. We'll see. Hopefully the 13.4 and 13.5 ones that I posted worked out well, and we'll be able to continue to have videos that are not blurry anymore. So that's very exciting. So today is tangent planes and differentials. You have done something similar to some of this stuff in 3.11. 3.11 you did linearizations and differentials. Here we're going to also be doing linearizations and differentials, but we're starting with tangent planes first. So when we get to the linearizations and differentials, if you don't remember that from Calais, you may want to go back and review it. Again, it's 3.11 as the Calais version of it. Okay, so page 731 is where we're going to start. And at the top of the page, here in this figure 13.32, it tells us that the gradient vector, which is what we were talking about in the last section, is orthogonal to the velocity vector. And so all the velocity vectors lie in a common plane, and this common plane is called the tangent plane, and that's where we're going with it. So remember from 11.5, to have the equation of a plane, you need a point in the plane and a vector that's orthogonal or normal to the plane. And so here the gradient vector is orthogonal to the plane that contains all of the velocity vectors. And so the gradient vector can be your normal vector, that lowercase n vector that was in the formula in 11.5. So here they talk about it just a little bit more. And then they have in this definition, sorry, I got a shadow. Okay, the tangent plane at some point to some level surface is the plane through that point normal to the gradient vector. And then here they talk about this is the normal line as opposed to the normal vector. So the normal line, the easiest way to think about that would just be the line that goes through the normal vector. Here they talk about it being parallel, but usually when they draw them, they have it going through it. So here we have the equation for the tangent plane, and there's actually two formulas for the equation of the tangent plane, so I highlighted this portion of it here so that when we get to the next one you can compare and see the difference. This particular tangent plane formula you'll use when you have a function of x, y, and z equal to some number. So it would be like, x plus y plus z equals 7 or something like that. That's when you're going to use this formula. We have another formula that we'll use in a different situation that we'll get to later. But here you have, for like slopes, you have the partial derivatives, and then you have partial derivative at x times x minus x naught, partial at y, y minus y naught, partial at z, z minus z naught equals 0. And then here, notice the equation for the normal line. This is from 11.5, the parametric equations. Right, these are parametric equations from 11.5, but notice that the v1, v2, v3 in this formula, they are coming from the partial derivatives. Okay, so these are our formulas. Our other formula for the tangent plane, here they call it the plane tangent to the surface, so it's the same thing. This would be what you would use if it's solved for z, z equals a function of x and y. So the other one, it had x, y's, and z's all mixed together equal to a number. This one you're going to use if it's z equals a function of x and y. And so here, the formula, notice the same kind of pieces, partial derivatives times x minus x naught, partial derivative. But here, for the z piece, there's no partial derivative in front of it, okay, because it's of a different form for this equation. So this is the other one. So whenever you are doing the tangent plane, you have to decide which of these two formulas to use, and you can tell by the way the problem is presented to you. Okay, and then here we have how to estimate change in a particular direction. So the problem would say something like, how much would this change if you moved blah, blah, blah. That's kind of how it would be worded. So here you have to estimate the change of a function when you move this ds. This is a very small distance. So it's just something like 0.1 or 0.2 or something. They'll give it to you. And so you're going to move from a point in a particular direction. So when they give you the direction, they'll either say from this point to this point, and you find that vector, or they'll say from this point in the direction of this vector. But notice here you're using a directional derivative, so that vector needs to be a unit vector, and you're going to do what we were doing before for the directional derivative, the gradient vector dotted into the unit vector, and then you're just going to multiply times this distance increment, this small distance, again, they'll give it to you. Okay, and then at the bottom of this page, where I don't know if I told you what page we're on, but 733. At the bottom of this page, it's talking about linearization, where we're going to. So we did linearization in Calais, and we used a line to approximate a curve. But here, this is talking, well, hold on, that's not what you can read that on your own later. But here, where it's talking about it? Okay, here we go. Right above example 5 on page 734. Before we used a line to approximate a curve. Now we're going to use a plane to approximate a surface. So it's just a higher dimension, the higher dimensional equivalent of what we were doing before. So before you had a curve, and so you used the tangent line to approximate it. Now we have a surface, so we're going to use the tangent plane to approximate it. So they talk a little bit about it here on page 734 in this figure, and then they have the formula here. So this is the linearization, one of the two linearization formulas. I'll show you the other one. This would be for if you have just x and y. So if you have a function of x and y, the linearization is the same thing basically as the equation for the tangent plane. So before it was the same thing as the equation for the tangent line. Now it's the same thing as the equation for the tangent plane. And so this is similar formula. This would be, it looks different, but it's the same. This would be the z naught piece, right? This would be the z naught piece, and this would have been like the z piece. And so if you move this over and have it equal to 0, then it looks like the other one. So the linearization is approximately equal to the function. So you can use, again, the linearization to approximate the function. And then skip this stuff at the very top, just this top little paragraph here at the top of page 735, this error, just this box basically. We're not going to be doing error, so you can ignore that. But we are going to be doing differentials, and so that's also on page 735, but it's toward the bottom. So differentials you would have done in Calais again, and it was dy equals the derivative times dx. It was just another way to write derivatives. This is the same kind of thing, but now we have partial derivatives. So you have the dx and the dy are just going to stay a dx and a dy, so you've just got the partial times dx and the partial times dy. Is for the differential. Okay, and then here we have the other linearization formula. This is page 736. This would be for if you have a function of x, y, and z. So notice here they're just using p sub 0 instead of having to write it out because it's 3. It's a triple. It is a order triple, not an order pair. So it's easier to just write it like this. But it's the same formula, just with an extra piece on it. And then here's the differential formula for a function of 3 variables. Again, just an extra piece on there. So all of this is right above example 8 on page 736. Excuse me. Okay, so let's look at it here in my notes. Just pretty much the same thing, but these are all the formulas. So we have the tangent plane, what it is, the normal line, what it is. These are originally from 11.5, but now with the notation with the partial derivatives, which makes it the chapter 13 part of it. You have the tangent plane and the normal line. This, remember, is version 1 of the tangent plane. Down here, version 2 of the tangent plane. Again, this one would be if you have z as a function of x and y. This would be if you have x, y, and z equals some number. And then estimating the change. I pretty much wrote this the same way as in the book, so there's nothing really new in my notes here, but just so you can see, excuse me, all of the formulas in one place. And so here again, just a reminder, this is a tangent plane approximation instead of a tangent line approximation. So when you find the linearization, you're finding the tangent plane. I don't know what is going on with my voice this morning. Okay, and then differentials, linearizations, and differentials in higher dimensions. So again, just pretty much the same as what was in the book. So these are all the formulas. Now we're going to look at some examples. So first we have 1 through 8. And it says, find equations for A, the tangent plane, and B, the normal line. So we're going to do number 4. So notice here, this is a function of x, y, and z equal to a constant. So we're going to use that first formula. And so the stuff that's equal to the constant, that would be the f of x, y, z. So f of x, y, z is all that stuff on the left. So we're going to start by finding the partial derivatives and their corresponding values at the point. So this would be the partial derivatives, and then we're plugging in the point p naught, which is 1 for x, negative 1 for y, 3 for z. So find the partial derivatives, plug in, and then you're getting these as numbers. So f sub x is 0, f sub y is 4, f sub z is 6. All right, and so here's the formula. This is, again, the first one because we have a function of x, y, and z equals a constant. We plug in all of our pieces, and then you can write this either way. It doesn't really matter. Sometimes the book puts the number over here. Sometimes the book puts the number over here. I always put the number on the right. So I like to put the number on the right, have all the variables on the left, the number on the right. Is the way I like to do it. But if you want to leave that number on the left, that's fine too. And here you can leave it like this, but because they all have a factor of 2 in common, you could divide everything through by 2, and you can get it down to this. So any of that would be fine. And that would be the tangent plane. Okay. Now for the normal line, you're using the parametric equations from 11.5. Okay, so for parametric equations, the point is the left side, and then the vector, or not vector, sorry, well, you could write it as a vector, it'd be the gradient vector, but I didn't write it as a vector, so it would be the partial derivatives, or the components of the gradient vector. That would be the things in front of the t's on the right, and then you're just simplifying. So for the tangent plane, it's going to look like this. For the normal line, it's going to be parametric equations. Okay, let's look at the next group of problems. 9 through 12. Find an equation for the plane that is tangent to the given surface at the given point. So that's just another way of saying find the tangent plane. So here, notice what we have on this one. Z equals a function of x and y. So if we have z equals a function of x and y, we're going to use that second formula. Okay, so you're going to use the second formula. It was on page 732, since it's z equals a function of x and y. So my f of xy is the thing that z equals, because z and f of xy are the same thing. So again, I find my partial derivatives, and I plug in my point because I want my partial derivatives as numbers because they're representing slopes here. And then, hold on, turn the page. And then again, I'm using this different formula. So here's the formula from 732, okay, that second formula. So plug in all the pieces where they go. Notice that this one is minus. When you do the z minus z naught piece, it's minus. And so you're going to have to distribute that negative. Okay, so again, I like to put my number on the right, but sometimes the book puts it on the left. So it's not like right or wrong. I like it better on the right. Personal preference kind of thing. All right, so that's the tangent plane using the other formula. All right, now let's look at the next group of problems. 13 through 18, find parametric equations for the line tangent to the curve of intersection of the surfaces at the given point. So notice here, you have two three-dimensional surfaces. You've got, we'll just look at 13 for example. That's not the one I'm going to do, but see how here you've got a surface and then another surface. And so what they're saying here is if you intersected these two, so this one is, I don't know, some sort of three-dimensional surface. This one is just a plane, right? X equals 1 would just be a plane. So you can kind of imagine taking that surface and, well, here, let's look at one. Well, no, never mind. Never mind. There wasn't one like I wanted. Anyway, I was looking through the other problems and I can't find one I want. So anyway, the plane, you can think about that like a piece of paper. If you just take a three-dimensional surface and you intersect it with a piece of paper, let's see if I have a picture. Yeah, like this. If you take a three-dimensional surface and you intersect it with a piece of paper, then see how you get, in this case, this ellipse, it's a two-dimensional curve in that case. The intersection between the two three-dimensional surfaces is a two-dimensional curve, in that case, an ellipse. And so what they're wanting you to do then is find the parametric equations for the tangent line to that curve. So if it's tangent to a surface, you'd have to use a plane. But if it's tangent to a curve, then you use the line. So that's why this one is a little bit different. You don't actually have to find the curve of intersection. You could, but you don't have to. Okay, so like let's say you wanted to on number 13. You could plug the x equals 1 in here, and then that would be a 1, so you'd move it over here with the 4, and then it would get it down to 2 dimensions. But you don't have to do that to be able to work the problem. All right, so I did that here just so you can see. You don't have to do that. It's not required. It's not necessary for this problem, but just if you're curious. Oh, sorry, I forgot to tell you. This is number 16. I guess that's pretty obvious because there's a 16 out there, but this is number 16. And again, this part of it not needed, just if you're curious. This one, it would intersect in a line. The birds are very loud this morning. I don't know if you can hear them. I'm in my sunroom, and the birds are chirping like crazy. Can you hear the birds? Probably not, because you guys have a hard time hearing me, and I've got the microphone right here. But the birds are super loud. They're driving me crazy. Okay, anyway, I'll be all right. Let's look at this problem. Okay, they talk about this somewhere. Hold on, let me see if I can find it in the book. If not, you'll just have to trust me that it's in here somewhere. Yeah, you'll just have to trust me it's in here somewhere. I don't know where it is. But here I wrote it down for you. So the tangent line is orthogonal to the gradient vector from both surfaces. So we looked at that a little bit, how the gradient vector was orthogonal to the plane containing all the tangent vectors. So it's the same kind of principle here. But here you have two surfaces, and so the tangent line is orthogonal to both of the gradient vectors that correspond to those surfaces. And so if you did the cross product between those, if it was orthogonal, then the cross product is orthogonal to the vectors that make up those. So if it's orthogonal to something that's orthogonal, then it would be parallel, right? So if that doesn't make sense, you can try. I probably can't hold my phone and do this. Let me see, hold on. So if you had, let's say this is a plane. You had a vector orthogonal to the plane. Hold on, I'm going to try to hold this and my phone at the same time. And then you had another vector orthogonal to that vector. I don't know if you can see, but try this on your own. See how this vector, this one that's moving, see how this is now parallel to the plane? Because if you have the plane, and then a vector orthogonal to that plane, and then a vector orthogonal to that vector, see how the vector's orthogonal to the plane now? You can try this on your own if you want to. I can't get my hand far enough away for you to see it, but anyway, then this vector would be parallel to this plane. So that's kind of what's going on here. So the cross product between these two gradient vectors will be parallel to the tangent line. And for lines, remember, for lines you want a vector parallel to the line and a point on the line. And so the cross product of these two orthogonal vectors would be orthogonal to those orthogonal vectors, which makes it parallel to the line. So hopefully that makes sense. I don't know, that's a lot of crazy words, but so here for our surfaces, you have, these were the surfaces from up here, this and this. And so you have this equals 2. If you move the 2 over, well, you don't really have to do this. It's going to go away anyway. It's not a big deal. But here would be your function equal to 0. But, you know, get it in equal to 0, you would have this for your f function and then this for your g function. So these would be my functions. I'm going to be taking derivatives, and when I take derivatives, the constants are going to go away anyway, so that's not really a big deal. All right, so here I have found my two gradient vectors. So the gradient of f, and then I plug in my point, the gradient of g, and then I plug in my point. And so now I'm going to do the cross product between those two vectors. So I've got the cross product between f and g, and that gives me this vector. Okay, so again, that vector is parallel to the tangent line. And then I have this point. So here's the point on the tangent line. Here's the vector parallel to the tangent line. I'm using the notations from 11.5 here. And so using the parametric equations, again from 11.5, it was x equals x naught plus v1t, y equals y naught plus v2t, z equals z naught plus z3t, and so it simplifies down to this. So this would be parametric equations for the tangent line. So these problems, again, you're finding two gradient vectors, doing their cross product, and then using that to get parametric equations for the tangent line. Okay, so hopefully that makes sense. Let's move on to this estimating change. So we're going to look at number 20. It says, by how much will this function change as the point moves from the origin a distance of 0.1 units in the direction of 2i plus 2j minus 2k? All right, so I've written that down here. First, remember, whenever you talk about direction, you've got to have it as a unit vector. 2i plus 2j minus 2k is not a unit vector, so you've got to make it one first. And here I'm using the notation that the book uses, this p naught p1, because sometimes in some of the problems, instead of giving you the vector, they give you the 2 points. And so this is just a visual reminder that this vector either can be given to you like it was here, or they can give you the 2 points and you have to find it yourself. So what you call it is not important, but it is important that you make it a unit vector. So find its magnitude, which is 2 square roots of 3. divide it by its magnitude, and simplify. Make sure to simplify always. So cancel out the 2's, and you get this u vector, which is, again, a unit vector. That was kind of the whole goal. So we've got it as a unit vector. All right, so now we need to find the gradient vector. So here's my function, e to the x cosine y. I want to find the partial derivatives. What in the world did I do? Oh, I didn't actually write. Oh, I see what I did. I did do it. I didn't write the function. That was my partial derivative. I thought I was rewriting the function. Sorry. That first derivative is the same thing as the original function. So, okay, I figured that. Here's my function. This was already my first partial derivative. I see now what I did. It didn't change anything because it's e to the x. So this is already my first partial derivative. I found it as a function. Then I'm plugging in my point, so it ends up just being a 1. Then I do my next partial derivative. So this is my f sub y as a function. Then I plug in the point at 0. Then I find my f sub z as a function, plug in my point, and it's also 0. So that gives me my gradient vector. The gradient vector, remember, is the vector made up of all the partial derivatives. Okay? And so this is the gradient vector at this particular point, so I've plugged in the numbers. All right, and so now I can do my directional derivative. Just in case you forgot the formula, hold on, I guess that would have been helpful. Where is it? This one. This is the formula that I'm using on page 733. This estimating the change, I have the directional derivative times the distance increment. So for the directional derivative, I have the dot product between the gradient vector and the u as a unit vector. So that's what I'm working on here. Okay, so we have the gradient vector. We have the vector that gives us our direction written as a unit vector. We're doing the dot product between them. And so this is the directional derivative. So directional derivatives, remember, are scalars. That's my directional derivative. And then now here's the formula. I wrote it down here finally. This is on page 733 again. So I have the directional derivative, which I just found, times this little bit of distance that I move. I just multiply those together. This would be your answer for a test because you can't use calculators. But just to give you an idea of the size, I did it on my calculator so you could see. So it's very small because you're estimating change. And so it's a very small change because you made a very small move. Okay, next. Turn the page. So page 738, we are now doing linearizations. Okay, so linearizations, it says find the linearization of the function at each point. These would be the two-dimensional linearizations, the f of xy. And so that formula, hold on, is here on page 734. So page 734 is the linearization formula for functions of two variables. So that's what I'm using. All right, so I've got to find my, oh, sorry, I thought I heard my dog scratching on the door. She scratches on the door when she wants to come in, but that wasn't her. So who knows what that was. Okay, anyway, we need, for the formula, we need the partial derivatives, but we also need the function value. Okay, so a function value you get when you plug in the function. Sorry, when you plug in the point into the function. So plug the point into the function, and that would be the function value. Okay, so then I need my partial derivatives. So partial derivative with respect to x, then the partial derivative with respect to y, plug in the point to get those numbers. And so here's the formula again on page 734, and then I just put the pieces where they go. So here's that y value that I found, partial with respect to x, partial with respect to y, simplify, and it would be this. So here, because you have this you have this L of xy on the left, then you do need to leave your number with your variables because like on the other ones you have equal to 0. So if it's equal to 0, you can move the number over to the other side away from the variables. But here you have equals ln of x, so you can't move it over to this other side. So you've got to leave the number with the variables. So that would be, I don't know why I didn't circle that. Hold on, that's going to bother me that my answer is not circled. You should always circle your answers to make it easier to find them. There, much better. Okay, so now it's the same thing but at a different point. So different y value, so I'm plugging that in to find my y value. Notice my partial derivatives as functions, they don't change, but I'm plugging in a different point, so their values will change. So here it's just all a bunch of zeros. So it's just ln of x. I mean, not ln. Why do I keep saying ln? It's L of xy equals 0 for this one. So it's the same thing at two different points. So it's going to give you two different values. All right, so that's linearization. Next group of problems, linearization in 3 variables. So find the linearizations of these functions, functions of x, y, and z. The formula for that is on page 736. It's here. In number 1, that would be 4 functions of 3 variables. Same thing, just an extra piece. All right, so again, we start by finding the function value. So we plug it into the original function and get the function value. Then we need the partial derivatives. All right, so there we go. We have the partial, and here I put little dots beside them because this is part A at one point. Part B is going to be a different point, but I'm going to be plugging them into these same partial derivatives. So I put little dots beside it so I could find it later because I can reuse the functions. I just have to plug different numbers into them. So this would be the partial with respect to x, and then I plug in this point for part A and I get 0. This would be the partial derivative with respect to y. I plug in this point for part A and I also get 0. And then this would be the partial derivative with respect to z. Plug in this point for part A and I get -1. So for my linearization, here's my formula. So this is, again, the 3-dimensional version of it. Plug in everything where it goes. Hold on the next page. And it simplifies down to just 2 minus c. All right, so for part B, here's my different point. So I need a different function value. Okay, so my function value has changed. What was my function value? Probably was 0 too. No, it was 1. Now it's 0. So it has changed. Okay, so here I'm reusing the functions from the previous page, but I'm plugging in different points. So I'm getting sometimes different values. And then I plug it all in and it simplifies down to just 2y. All right, so that is all from 13.6. Let me just warn you, 13.7, ridiculously long. So don't wait till the last minute on 13.7. It is crazy long. But if you have any questions on 13.6 or the new way I have started uploading videos with this new app, let me know because I'd love to know if it's not working. But if it's working, I plan to keep using it because it is fan-stinking-tastic. So if you have any questions, just send me an email.